have additional position like nodal officer for RUSA 2.0, Osmania University, Ministry of HRD, Government of India, since to design, additive manufacturing, 3D printing centers, Center of Excellence of Osmania University. He was the head of the in charge in mining engineering, University College of Engineering, Osmania University. He has held many positions like control of examination from 2018 to 2021. He was director for internal quality assurance cell, IQSC, Osmania University, 2016 to 2018. He was director for University Foreign Relations Relation Office from 2017 to 2018. He was head of the mechanical engineering from 2013 to 2015. He was chairman for the Board of Studies in Mechanical Engineering. He was additional controller of examination from 2005 to 2009. He has guided many doctoral students. He was the member of NAC, UGC autonomy members. So he had teaching experience and research experience more than 20 years, 28 years. His area basically is related to additive manufacturing, computer aided modeling, design and analysis, bulk solid handling. He has published more than 115 international and national journals. He has awarded many honors and recognition. So I'm just reading some key awards like he has awarded with Bharat Ratna Mukhyangunam Viswasaraj Award by Government of Telangana and Institute of Engineers. He is a state level best teacher by Government of Telangana, and in 2019 he is distinguished alumni by Kids Warangal in December 2016. Many things are there. So with this, I invite Professor Venkatesh to start the session.
So let me thank you for giving me opportunity to share my experiences in the 3D printing. Let me know whether I am audible or not first.
Yes, sir. Yes, sir. You are audible, sir.
Okay, and just I want to share my screen. Is it okay?
Yes, sir. It is. Yes, sir. It is visible, sir.
Is it full screen?
No, sir. Full screen not coming, sir. Please make it full screen.
So how can I make it full? I don't know. Okay. Here.
The right, sir.
This is a full, no? But
no,
left side is visible. Something is visible, no?
Left side is visible, sir. Just one minus sign is there, sir. Before the minus sign, if you click, then it will work, sir. Third one, sir. Second, third.
This one?
No, sir. That minus sign is there. Zoom in, zoom out.
Here?
No, in the bottom, sir. In the bottom.
Yeah, this one is there.
No, just below that icon is there. No? If you click there, it will be full screen. Just below.
Automatically it should come now.
Or else I think F5 if you press, I think it will be.
Sir, we can press F5, function 5.
Pardon me?
Function 5, function key 5 we can press, sir.
No,
Okay, maybe we disconnected. Yes, sir. Your slide is visible, sir. Sir, can you hear us?
It is also half screen, no? Not full screen.
Not full screen, sir. So press F5 will be option out there, no, in the
I
keyboard.
already pressed.
Okay. But I think when we are pressing F5, it is disconnecting.
It would be in PPT, not here, I think.
In PPT, yes, sir.
Not here.
No, you are here, but PPT is gone.
PPT, but I don't know why this. Same thing. Hello?
Yes, sir. Yes, sir.
Ashit, is it audible now?
Yes, sir. Your voice is audible, but
Voice is audible, but here
presentation is not coming, sir.
Presentation window is there, Chrome tab, window, and entire screen.
You can make entire screen, sir.
Entire screens, if I select now,
Yes,
only
sir.
this one is coming. Window.
The PPT need to be full screen, sir.
Why? I don't know. First time I'm observing this problem.
Yes, sir. Your full screen is available now, sir. You just open the presentation and put Control plus, sir. It will get increased. That's enough. We can proceed.
No, this is inactive. This Nalla Malla Reddy inactive.
You may right click and open it. If it's fun. Try for it.
No, it's exit full screen. Save as, translate, print. I don't know why. Okay, I will manage with this. I think only half screen is coming. I don't know why. Escape.
So
Actually,
the last one, fourth one.
Sir, in
Yeah.
the bottom, fourth one.
The
sir.
last button, fourth one, sir. Fourth one is full screen, sir.
Before,
Below to
before,
that. Below
before
to
the
that.
minus, before the minus, that icon you need to click, sir.
No, that is no, that is actually in PPT.
Yeah.
Once it is
Yes.
shared, it is not active.
So then you can make it control plus, sir. Automatically it gets enlarged. That's enough.
Control.
Control plus.
Control plus.
Control. Hold the control button and press the plus button, sir. Plus is in the top, sir. Control at the bottom. In your keyboards.
Yeah. I'm doing same thing. Is minus. Is it visible or not? No, but little.
Yes, sir. Is it visible, but a little. We can start.
I'm surprising actually. This why it is inactive.
Okay, sir. You can proceed, sir. You can proceed.
This is exit and entry. Exit full screen. This, but why something is changing? This actually before minus, that is actually full screen, or F5, that is in the PPT, but it is not active here.
Or else just close it again. We'll open it, sir. If you try for reopen again.
Okay, once I will open it and stop screening, and again I will share. This is also small.
Okay, sir. You can proceed, sir.
Let me once I will try. I will manage with this.
Sir, that itself is visible, sir. You can proceed, sir.
So just seeing layout. No, this is not. Okay, I will proceed. I don't know. Sometimes what happens? So I don't know why it is not coming.
It's okay, sir. We can start, sir. It is visible, sir.
So whether actually I'm scrolling out or up and down also not working. No. Stop sharing.
I think if you click second slide, it will come. I think maybe the keypad is not working.
Not that actually. It is working actually. Since long time actually there is no usage of this system. Slides. Only the screen is sharing.
Yes, sir.
But
The slide is not moving, sir.
Slide is not moving up and down.
Okay.
Okay. Once I will do one thing. I will.
Or else, sir, if you please share the file, I can present from my side.
Button no to share this one. Share screen. Yeah,
Yes,
Mr.
sir.
Rachit.
Yes, sir. Yes, sir.
This is the only button. Nothing is there. But and I'm sharing. Then afterwards, the site will be able to see the contents of your screen. Only this one.
Okay.
Just sharing. Selected. To avoid an infinity mirror, don't share your entire screen or browser window. Share just a tab or a different window instead.
You can share entire screen, sir. That's the best way.
Anyway, share anyway. Just this is the only the thing coming, and I'm enlarging. But
If the slide is moving, sir.
slide is not. That is a funny
Okay.
thing.
Slide is also not moving, sir.
Not moving up and down. The first time I'm experiencing. Stop sharing, meet window and hide. The first time I'm experiencing like this. Many. I don't know. Shall
Hello, sir. Sir, if you please send to me, I can present from my side so that I can make it, sir. Sir. Yes, sir. Maybe some. Yes, sir. Yes, sir. Maybe something, some problem is happening there. Okay. Yes, sir. Now, yes. share screen is visible. Yes, sir. Yes, yes, yes. Yes, I'm able to see your screen, sir. Dear participant, please wait 1-2 minutes. We are starting soon.
Asit sir.
So please wait for 1-2 minutes.
Asit
Please
sir.
sending that. Sir.
Asit,
Ramesh sir.
make sir as host.
Okay.
Make sir as host first.
Yeah, Mr. Ashit,
Yes, sir.
did you made me host or not?
Sir, I'm making that one. No, sir, I am not making that.
Without that, how can I? There is a problem. Actually, I'm surprising.
Okay, I'm doing, sir.
Yeah, you make me host. That's the problem.
Yes, sir. Yes, sir. Yes, sir. I'm ready.
Now we made it?
Yes, sir. Yes, sir. Please try it again, sir.
I will try once again. All presenters must be host.
Yes, sir. Screen is coming.
You made me host?
Host, yes, sir. Sir, check, sir. The slide is moving or not, sir?
Again, not moving. Not moving. Okay, I will share your.
Yes, sir. Please share with me. I will.
Okay. Shall I send a PDF?
A PDF, sir.
Otherwise, difficult to share.
Yes, sir. Any format you can send to me so that I can.
Yeah, shared with you.
Just 1 second, sir. Yes,
Sachin.
sir. Yes, sir. Yes, sir. It's coming, sir.
Yeah, shared with you.
Yes, just downloading.
So good afternoon to, good evening to one and all. Sorry for the delay. Actually, I don't know, some unexpected. Am I audible, please?
Yes, sir. Yes, sir. You're audible, sir.
So unexpectedly, this I don't know why. All the time I'm sharing with my laptop only. I don't know what happened, but I will just.
Yes, sir.
Okay.
Is it visible, sir? Screen
Yeah,
is visible?
but not full screen.
Because you have sent that. Okay, let me full screen.
PDF copy only, no?
Oh, yes, sir. This is PDF only, sir.
But are you able to scroll down up?
Yes, sir.
Yeah, now it is okay.
Now, okay. Yes, sir.
You are able to scroll up down.
Yes, sir. The
But
screen
it is
is
not full screen actually on the monitor.
But from my monitor is showing full screen, sir.
It is full screen.
Yes, sir.
Okay.
Yes, sir. It's full screen, sir. Okay.
Okay. My monitor I have to change. Okay, because in my monitor, I think there is a problem. I think in my monitor is only showing half of it. So good evening to all of you. My topic is advancements in additive manufacturing, that is 3D printing. As I explained or introduced by Mr. Ashita, I was the founder director of Center for Product Design Development Additive Manufacturing in Usman University. And at present, I'm Secretary Telangana Council of Higher Education. So I want to share some experiences with 3D printing, particularly what is happened and what is happening in the area, and in the center, in particularly Usman University. So next, please. So my overview of my presentation is additive manufacturing, the definition, what is meant by that, and also what is I think this is not covered by anyone, Mr. Rashid. Any lecture has given?
No, sir. It's not covered, sir. This one.
Okay, it is not covered, then I will touch. If
Yes,
it is
sir.
covered, I will skip some of the things.
Okay, sir.
Means
Not covered, sir. No,
additive
it is not covered.
manufacturing.
Yes, sir.
Additive manufacturing, anyone has covered?
Yes, sir. Mr. Rakesh, he has covered the sustainability part of 3D printing.
Okay.
So he has not covered this basic thing.
Okay, the basics.
You can cover, sir. Yes. Sir.
Yes. My presentation goes like this: need for additive manufacturing, inputs and methodology of additive manufacturing, and also steps involved in additive manufacturing, and AM processes, and in particular SLS and SLM AM systems what we have in the lab. And Rakesh is Mr. Rakesh is also working in NCAM, National Center for Additive Manufacturing, that is NCAM. And the purpose, because of our center only, the NCAM is situated in Usman University beside the CPDDAM. CPDDAM means the Center for Product Design Development and Additive Manufacturing. So in this area, we are working from 2009 onwards. So that is the reason the National Center for Additive Manufacturing having the commonality in research. They have established the center at Technology Development Center, Usmania University, Hyderabad. Next, please. And my definition for additive manufacturing, two definitions are given here. First definition would be very appropriate and apt. What is additive manufacturing? a technology that produces models and prototype parts from 3D CAD model data, CT and MRI scan data, and model data created from 3D object design systems. So what do you mean by this? There are three types of data are given to the 3D printers. First type of data is CAD data, model CAD, 3D CAD data. That means by using any one of the softwares like CATIA, ProE, whatever the 3D CAD softwares are there, no, by using them, we need to generate the model. That is called 3D CAD model data. CT and MRI scan data means which gives the patient specific data given by the doctors. So CT, computer tomography, MRI means magnetoresonance imaging. So these two data are given by a doctor pertaining to a particular patient. And third type of data is 3D object digitizing systems. That is nothing but existing software, existing model is there, existing physical object is there, that we are going to scan by using 3D scanner and digitize into 3D model again. Those three types of data are given to 3D CAD model, 3D printing, then when manufacturing. That is called additive manufacturing. Additive manufacturing means is a layer by layer technology, one layer upon other layer. So irrespective of these three types of data are being processed and built by layer upon layer. So that is why layered manufacturing, additive manufacturing, electronic manufacturing, digital manufacturing, and additive manufacturing, all these are synonymously we are using. So another definition given by Joe Beeman is direct fabrication of parts, components, or models from 3D CAD model drawings without part specific tooling and human intervention. So that means just we are giving a object or sending a file to the 3D CAD model, a 3D printer, and just closing the shutter, the door, and without any jigs, pictures like what we use in conventional manufacturing methods and tooling, without any human intervention, automatically it manufactures. That is another definition given by the Joe Beeman. And the final conclusion is rapid prototyping or additive manufacturing. So earlier we used to call this type of technology as a rapid prototyping. Rapid prototyping is how best we are going to produce the prototype within short time. The rapid means within short time, that is called rapid prototyping. But the rapid prototyping word has been changed to additive manufacturing because rapid prototyping is only prototyping, but additive manufacturing is not only prototyping but also actual and functional manufacturing of the components. That's why the broad word and universal word is additive manufacturing. And sometimes interchangeably in this presentation we use rapid prototyping or additive manufacturing or digital manufacturing or electronic manufacturing, but it are one and the same. So it is nothing but conceptualization to realization. So whatever the idea in your mind, whatever the design having in your mind, and innovation you are having in mind, that you are going to realize in the form of 3D print out. That is called a conceptualization to realization. That means whatever the idea you have, you are realized and conceived your dream, your visualization in the form of physical output. That is nothing but a rapid prototyping or additive manufacturing. Next, please. So what is the need for AM? Quality is a major concern. Productivity, how best we can produce with less time, within time. Reduced cost. Reduced cost means suppose if you are directly manufacturing without any prototypes or any additive manufacturing, there is a problem of end product defects. So those defects will be incurred in the losses, like that product will go waste with the errors. So that is why for reduced cost also we use additive manufacturing. Reduced costly errors. So what are the errors present in the system, in the product, can be eliminated by using additive manufacturing, because additive manufacturing is in between method for between the design and final manufacturing. So before final manufacturing or end product manufacturing, end results, we reduce the cost by looking at the rapid prototyping or otherwise additive manufactured component, by looking at physically and reviewing the design and showing to the peers. And ultimately, it should give a satisfaction to the customer. So every manufacturer, every product must be satisfied with the customer. Then only it is saleable. And global competition. So because of the global competition, the vendors or the manufacturers have to follow how to adopt this additive manufacturing into their cycle of operations, so that they can reduce the errors, they can minimize the time per production, they can satisfy the customers, and also they can earn the money, earn the profits. And all the time, the finally, the additive manufacturing leads to time to market and finally results in product development. So time to market also will be reduced drastically if we use AM in the industry. Next. So as you are aware, the just now in the definitions there are three types of data are given. So the inputs for additive manufacturing are, one is CAD/CAM data, another is medical data, third one is re-engineering. That is, we have said the 3D digitizing objects. So first one is CAD/CAM, means that is 3D model data. Medical data means CT scan MRI data. And third type of data is re-engineering. That means already existing component is there, that we are going to scan it and convert into again 3D solid model and sending it to the 3D printer for production. So these three types of data are used. But irrespective of these three types of data, but all the 3D model, 3D CAD models, 3D printers accepts the files in the form of STL. STL means stereolithography. Short form, the three letters are taken from the stereolithography. .stl. Some abc.stl file has to be sent it to the 3D printers. So then afterwards, what happens? The scans and converts this STL file into layered file. So it will slice into so many layers, like how the bread has been cut into so many slices. Similarly, initially it was a 3D solid model in the form of STL. So from converting from your CAD model to STL, what happens is the 3D volumes have been converting into a tiny triangle. Those tiny triangles are packed, and it will be stored information like three vertices like X, Y, Z. So X1, Y1, X2, Y2, X3, Y3, three vertices are there. Why only triangles? Why not other? Because the triangle is the lowest area and also used to minimize the transmission errors from CAD model to the STL file. So this STL file is then processed and then will be layered by using third-party softwares, so many layers. And those layers have been stored in the system, computer, and then the 3D printer will build layer by layer technology. So all the layers are almost all same thickness, but there are the 3D printers which permits variable layer thicknesses. So 1 centimeter layer is some 0.1, 0.2 like that. Other one is 0.3, 0.4 like that. we can have a variable layer thickness depending upon the technology, depending upon the machine what we are going to buy. And all the machines in the world understands only the STL files so far. Okay, it will not recognize the CAD file. CAD file will be having different extensions like Pro Engine is having PRT, and some other files are giving some extension. And but the 3D printers will recognize only STL file. Next, please. So these are the STL editing softwares. So Rhino, Magix from a Metalize and Desktops and Solid View. These are the third-party softwares which processes the STL file. Next, please. And this is the methodology used in additive manufacturing. So the methodology involved, there are few steps are there. First is whatever the idea you have in your mind, that has to be put in the form of a CAD model. And this is the time consuming step, because depending upon the complexity of the model, it takes some hours to days and weeks to construct the model in softwares like Unigraphics, SolidWorks, CATIA, ProE, etc. Okay, and that is the first step. Second step is the AIM machine processes STL file by creating sliced layer of the model. Okay, first step is creating model. Second step is that model has been converted into STL file, and then STL file has to be converted into layered file, layer by layer. So in the right side you can see, I will show this one. So they are the layers. You are able to see my cursor?
No, sir.
Because I'm not presenting. Okay.
Yes, sir.
Ashit is presenting. Okay. So then the third step is the first layer of the physical model is created. The model is then loaded by the layer thickness of the next layer, and the process repeated until the completion of layer. So in the platform, 3D printer platform, it will start building first layer. After building first layer, the platform fall down by one layer thickness, and over the first layer, second layer will be built. So like that, every time the platform fall down by one layer thickness after the completion of the layer, and third, fourth, like that, the last layer, up to last layer, we can build layer upon layer. That's why it's called also the layered manufacturing. In the additive manufacturing, sometimes some books are also called as a layered manufacturing method. The fourth one is the model and any supports are removed. The surface of the model is then finished and created. Sometimes we require post-processing of the model. Post-processing requires certain finishing, removal of the surface, the blurs, etc. It all depends upon which technology you are going to use, whether it is required post-processing or not. That depends upon there are 40 plus technologies are there. Out of 40 plus, we discuss only just popular technologies like SLM, SLS, and FDM, etc. Next, please. So these are the 7 types of AM technology, that sub-classification and companies. I will share this anyway. We can see, but there are something, they are not visible, but if you take printout or if you can enlarge, you can see there are 7 types of sub-classification as suggested by 3D hubs. So first one is the VAT polymerization, second one is material extrusion, third one is the material jetting, fourth one is the material binding, fifth one is powder bed fusion, sixth one direct energy deposition, last one is direct sheet lamination. So like this, so all the 3D printers have been classified into these 7 sub-classification. Under 7, again, depending on the company, so the all RN falls into one technology. For example, VAT photopolymerization. VAT photopolymerization, there is SLA, DLP, CDLP, and material extrusion, there is FDM. So like that, metal jetting, we have MJ, nanoparticle jetting, drop on demand, etc. So binder jetting, we have a binder jetting only one. So powder bed fusion, we have multi-jet fusion, SLS, DMLS, LBM. So like that, we have direct energy deposition, we have a lens and LBM. And the last one is sheet metal, we have LOM, means layered object manufacturing. Okay, we'll touch upon some of the technologies in detail. Thank you. Next. So these are the various technologies. I have shown the 7 types, but their summary under SLA is liquid based, SGC also liquid based, FDM is solid based, and LOM is solid based. And powder based 3D printing, lens, selective laser sintering, SLM, or these are powder based. So liquid based, solid based, powder based are shown here. Some of the materials are shown in the right side. And apart from this, we can also use some other materials, metals and non-metals. Okay, next. So just stereolithography. This was the first invention in US. Stereolithography in STL file also, we used to take 3 letters ST and L. ST and L. That is, every file has got 3 letters extension. Here STL file also we have ST and STL dot STL. So in this method, I think these are basics. Okay, I don't want to waste your time. STL file is very the basic, and this is simply the photopolymer metal is used here. That liquid photopolymer metal is when it is exposed to the laser, that is a scanning laser, and automatically it solidifies. So laser passes over the liquid which is there in the vat. That liquid will be having a property of whenever it is exposed to the light and energy, it will get solidified, and layer by layer it forms. Next. And fused deposition modeling. In the right side, you can see the filament of wire wound around the barrel that is passed through a nozzle. That nozzle is supported, is supplied electric energy, and because of the electric energy, that nozzle melts the filament of wire and pours in the form of 2D layer. So that is fused deposition modeling. Then next. Laminated object manufacturing. Here, instead of the powder and all, here we use a sheet. Like a sheet is having one side is glue, other side is free. So the glue side will attach to the each other by the laser. So laser will cut the sheet in the form of 2D contour. So because every 3D model has to be converted into 2D layer, that 2D layer form, it will cut, and the remaining material which is unwanted can be removed by using the form tools, and then other side of the barrel will wound the used paper. So this is mostly used by the civil engineering applications for making miniatures. Next. Actually, 3D printing. The name, the buzzword is 3D printing. No, 3D printing has come from this technology. So 3D printing is also one of the additive manufacturing technologies. In this case, the powder is bonded by using liquid adhesive. So liquid adhesive will be poured onto the powder, and because of the adhesive, the powder will be bonded each other and forms layer. So after that, the plunger fall down by one layer thickness, and further the fresh powder will be coated onto the platform, and liquid adhesive sprinkles over the powder, and because of the adhesive sprinkles, it forms the layer. But this is the lowest strength technology or 3D printing material. So out of all the technologies, the powders or the part produced from this particular 3D printing printer is very weak. Why? Because the strength will be depending upon the strength of the adhesive. How much bonding it creates, that is only the strength obtained by a component. Next. So select laser sintering, SLS. And here in the selective laser sintering, we have a carbon dioxide laser, and which is exposed, the powder gets exposed to the carbon dioxide laser, and the powder being used are polyamide glass filled, polystyrene. This type of metals can be used to expose to laser, that is carbon dioxide laser. In this particular machine, we have a Farmiga P100 machine. We use 30 watts power of laser power to sinter the polyamide powder. So here the fresh powder is exposed to the laser, and once the layer is formed, the plunger form the fall down by one layer thickness, and a fresh coat of layer will be spread over through reporter or blade, and then next layer forms like that. So first layer to last layer will be generated using the carbon dioxide laser. The process is called sintering. So sintering, the heating of material below the melting point, then automatically it will liquefy and then solidify, not completely melting. It is only sintering. So that means sintering means the melting point is, for example, 300 degrees centigrade. We heat it only 270, 280 below the melting point, and then we get it sintered. Next, please. So this is a data acquisition from medical data. So CT scan. There are two softwares we use in the case of medical data. One software is called Mimix, other is called Magix. Mimix is for medical data. Magix is for orientation, positioning, and the scale up, scale down purpose we use, and array and stacking purpose we use. So Mimix exclusively used by the medical data. The processing of CT scan and MRI data has to be done through Mimix software. And then we use again Magix, and we convert into STL and EY RP tools, and then the third-party sources we use for creation of job, and then powder is, for example, here it is called JOB is the job file, and SLI is the slicing file. Like that, each and every step, for example, in the case of 3D model, ProE extension is PRT. So that PRT is converted into STL. Then STL converted into SLI. SLI converted into job, So like jobs we give feed into the 3D printers, then those jobs will be printed. Next, please. So this is a typical picture showing the pyrometer. Pyrometers are eating the polyamide powder. That white color is polyamide powder, and we have to wait at least 1.5 hours to 2 hours to warm up the powder from room temperatures to sintering temperature. Next, please. So this is once a powder is obtained the sintering temperature, we can see the texture. The loose powder is white and the other one is brown, like it turns, and the sintering is taking place from XX direction and YY direction, so that the two layers will be perfectly bonded. Next. So after sintering, we remove the bin with the powder and eject the bin, and we search for the parts and then we clean. Next, cleaning will be taking place in the next slide. So like that, we can collect the powder, the parts which are submerged in the powder, and we clean it with the brush and also the blaster. Then we use it for further cleaning. Next. So this is the blasting, sand blasting. So for accuracy purpose, the particles attached to the sintered product also can be removed with the sand blaster. Next, please. So the advantages of selective laser sintering is one is the uniqueness of the SLS is it does not require support material. In the case of powder, plastic powder, in the case of metal powder, it is required. But in the case of plastic powder like a polyamide glass field does not require any support material, which requires in the case of even FDM, SL, the stereolithography, etc. Okay. And the finished products are sometimes functional and testable, and these parts are used as a functional components which the operating temperature is 100 degrees centigrade, because it melts at around 290, 300 degrees centigrade. That's why to avoid alteration of properties or elongation and all, this can be used up to 100 degrees centigrade as a functional components. Next, please. Okay, high mechanical and thermal resistance and the strength rigidity under the extreme conditions of high temperatures, and these can be used as a indirect patterns, direct patterns and indirect casting, durable metal parts, mold inserts, direct low density complex investment casting patterns can be prepared directly from CAD. So the parts produced from this SLS can be used as a patterns and makes the mold, and then we go for castings. Next. So limitations of selective laser sintering. So for anything, no, cost is the major one. That it has more cost and less strength. Accuracy is also more. And last three, strength, accuracy, finish. So out of 4, strength is moderate, but accuracy and the finish is very high. The cost also very high. But in the right side, I have shown a portrait. This much big 6 feet portrait can be built, making into pieces. So we can make this as a pieces. Though your machine is not able to build this much big portrait, but we can make them into pieces and then assemble, and with using the fits like what you call snap fit, or like male female fits, then we can assemble 4 or 5 parts into like this. So the limitations are mainly cost and strength. Okay, next. So these are the pictures which are used in the case of Formula P100. And the first one, the box is the x-axis is 200, y-axis is 250, g-axis is 330. The maximum build volume is 200 by 250 by 330 is the maximum build. And this costed us in 2009, it cost us 1 crore rupees. Next, please. So in the first case, no, effective building volume is 200, 250, 330. So now there are very big machines are available, but if you are able to spend 3-4 crores rupees, then you can have more build volume. Okay, next. Machine capability, layer thickness is 0.1 mm, and in the case of metal 0.02 mm, which will have more accuracy. In the same SLS, we have non-metals and metals. So the minimum wall thickness is 0.4 to 0.5 mm, and laser diameter is 0.5 mm. So the minimum wall thickness that we can build with this is 0.4 to 0.5 mm. Next, please. Next, this is not required. So in this method, no, there is a problem of shrinkage. So to maintain the accuracy, it is not that once you are purchased a 3D printer and you are building something which is not accurate, of no use. So to maintain the fits and tolerances, and the parts must be produced within the tolerances. So for that, no, to validate, there are some parts are there which are used for. First one is shrinkage allowance calculation. Second one is the mechanical testing. Next, please. So for example, here, these are the, in the right side, dimensions are, for dimensional accuracy, we have to build this, and then after building, what is the dimension? Before building, what is your model dimension? The difference is the loss, that is nothing but shrinkage. To compensate shrinkage, we need to give the calculated shrinkage in the machine, 3D printer. And the others are mechanical testing, wall thickness, etc. Next, please. So after calculation of the shrinkage, we need to compensate in X direction 3.2, Y direction 3.2, G direction 1.5, 1.8, so that after building, you will be getting within the tolerable tolerances which are specified. Otherwise, your part will be discarded. Next, please. So selective laser melting, so which is having at our center for product design, development, and additive manufacturers. Next, please. So this is the actually capability matters. All these are we are having at our Usmania University. Last but one is there is a 3D scanner which is having 33 lakhs rupees through. We use it for digitizing or 3D scanning. So first, second, third, fourth, fifth, sixth, and last one are the 3D printers. So we will see in detail. These smaller dimensions are there, but next, please. Yeah, this one is the selective laser melting machine. So it is imported from Lübeck, Germany, and it handles almost 6 materials. So we have 6 materials. Under 6 materials, again, there is a sub-classification. And this machine costed us almost 6 crores rupees, and which is there in the Usman University Center for Product Design Development and Additive Manufacturing. Next, please. So the left side is the sieve, right side the chiller. Next, please. And these are the materials that it can handle. So many students are doing PhD, and almost 3-4 PhD is completed. And the build volume is 280 by 280 by 365 maximum build volume. And we will see the materials which are used, almost 6 types of materials. Next, please. These are technical specifications. And the second one is 40 watts power we use for sintering purpose. Sorry, 400 watts. So in the case of previously plastic powder polyamide, 30 watts carbon dioxide powder, but here it is 400 watts power, laser power are used to melt all these materials. 1, 2, 3, 4, 5, 6 types of materials are there. Aluminum alloys, stainless steel alloys, nickel-based alloys, titanium alloys, cobalt alloys, and copper alloys. Again, we have sub-classification. But below materials available at CPDTM, what we have procured, 6 types from above. So from each category, we have procured that these materials are available with the center. And their strength we can calculate. There is a data sheets are given, and with this we can do some research work, like what is the porosity you are going to get, how to build the electrode discharge electrodes, like that. Next, please. So lattice structure. Another advancement in the 3D printer is use of lattice structure. Lattice structure usage is for two purposes. One is for supporting. For example, if you are building a 3D model by using particularly metal, so it requires, after melting, what happens, the density will be more. Powder form density will be less. After building, the density will be more. That dense layer cannot withstand by the powder. It will simply fall down. To avoid that, we use this type of lattice structure to retain the layers which are building above it. That is one thing. Second application is this type of lattice structure we use and we produce this and use it for biomedical applications, so that the tissues will pass through this and it will not prevent from tissues to grow from this porosity. That is the second one. So one is for lattice structure for supporting. Second one is the lattice structure we can use that structure for implanted into the dental or any other area, so that the tissues will not obstruct to grow. It will grow into that. That is one thing. So this type of structures will optimize the usage of support materials, so that we can save powder and save money. Next, please. So this is a typical example where we developed this using titanium. These 9 samples are being developed are produced using SLM, selective laser melting. And looking at the 3 positions, if you see the first position, it is horizontal. It requires less supporting structure. In the middle one, it is 45 degrees. It requires a lot of what you call support structure. And last one is 90 degrees, 0 degrees, 45 degrees, 90 degrees. So in which position you are going to keep, that matters in designing the support structure. At the same time, it also affects the surface finish going to be obtained in 3 areas, 3 different orientations. Next, please. So if you look at applications, aerospace applications, automotive, functional prototype, defense, military, tooling, medical, all these areas we are going to use this medical 3D printers. Next, please. So this is a selective laser sintering. If you look at the powder when it is exposed to the laser, 400 watts laser, and there is a sparks and fumes coming while building because of the high temperature applications. Next. So applications, coming to applications of additive manufacturing, I'm just touching upon all types of applications, not only the one type, mechanical engineering, all types of applications, because the additive manufacturing is now has become a interdisciplinary subject, and applications, if you look at, vast from all types of engineering, concept models, CAD databases, etc., etc. Next, please. Next, aerospace. So continuous. Next. Okay, electronics and communication. So you look at the your mobiles, all electronic gadgets. Initially, they were manufactured with the help of additive manufacturing. Once it is validated, it's a design, it's a aesthetics, etc. Validated, then we go for mass production by using any other injection molding machines. So, but otherwise, initially, for validation purpose, we have to produce by using additive manufacturing. Next. So one of the widely applications, widely used additive manufacturing application is biomedical implants. So looking at the pictures, left side you can see the skulls and all, but right side you can see they are the sports safety devices like knee braces, knee caps. So they are used for particularly sports safety devices for sports persons. And initially it was manufactured with this, but finally once it is validated, then final product will be with metal, so that it will give safety to the sports person. Next slide. So looking at the implants here, you can see titanium implants are there. A patient having some accident or malignancy, that type of structure or the area is scanned and made with the 3D printer, and then we can implant into the human being. So here knee joints, even teeth, and then here we can say these two skulls are, for example, two heads are collided or otherwise joined, and then surgical operation purpose also we use 3D printer, 3D printers. We produce the component with flexible material, and the doctors perform the surgical operations on the flexible heads and before going for actual surgery. So the purpose is after trials they will get accuracy in surgery. Next, please. So this is another application where the hand without the, we can say fingers and all, we can make fingers and we can put some sensors and we can make it operational like robo. Okay, next. So nowadays, no, many problems are coming for the even teeth removal, teeth root canal, or total teeth or some teeth. So doctors, what they do, they take the impression and they will ask you to come after 1 week, and then they get it manufactured somewhere by using 3D printers. But in Hyderabad also many printers are there which produces the teeth, and after that, no, doctor will simply implant into the patient. Okay, next. So automotive applications, there are so many applications are there. Here in this picture, we can see the concept, which are concepts are there, and are the creativity, roof dashboards and other. Once it is validated or reviewed, then we go for mass production in the case of even sheet metal, etc. Next. Same thing, same parts. This is concept car. Next, please. So castings. So castings, we can make patterns with the help of even powder, plastic powder, or otherwise we can make patterns with the help of metallic parts. So this is a pattern. So it will serve almost 50,000 to 1 lakh parts for casting purpose. Next. So in Coimbatore, no, they are using the sand molds, so which are sintered with the help of laser. Laser sintered sand molds are using for casting, which will give more accuracy and less timing, and also complicated shapes. So earlier we used to depend upon the women's manpower skills, but now once the model is there, that according to model, the female, they make mold, and that mold can be used for casting purposes. Molten model can be poured into the casting and we'll get the housings, so special castings, so motor blocks, pump sets, and etc. Next, please. So this particular slide explains the complexity involved in building the pump valves, control elements. The advantage with the additive manufacturing is that it does not have any assemblies. So if you look at the two components as a single component, it is produced with the help of direct metal 3D printer. So though it is metal, if you look at the conventional methods, no, we need to depend upon the CNC machines and also assemblies. And if you cut it, no, you can see a lot of intricate details are there, which will also give you more heat transfer and more the porosity, which will give you the cooling effect and having more internal channels, and which are built as a single go. Next, please. So this is a Formula One car specific parts. For example, if you want to manufacture one or two parts, additive manufacturing is easy. If you are going for mass production, then we have to go for conventional one. Next one. So this is another prime cast pattern. Left side is a pattern made by the 3D printer. Right side aluminum casting is made with this pattern, and this LML Limited Kanpur company, they use this 3D printer for producing the aluminum castings. Next, please. Similarly, this is for manifold, exhaust manifold. Okay, next. These are all steering wheel, fuel tank, etc., which are actually conceptual. These are conceptual. Once the concept is final and validated, we can go for even actual one. Next. So this is a Boeing light frames as per the 77 cabin and good statistics. And if you want to go for the making mold for this, is the costly. So since you need only one few parts, it is very economical using additive manufacturing by using the powder or sinter or whatever the SLM or SLS technology for producing few products compared to the conventional making molds and dies, tools, etc., which is very costly. Next, please. This is a turbine combustion chamber, which is made with nickel alloy, but this is for demonstration purpose. So you can see how much intricate details are there and finish and everything for aerospace applications. So particularly aerospace applications, we need high strength, low weight. So 3D printers are used, particularly metal printers, are used for producing components for aerospace applications where we need more strength and lightweight. Next, please. These are fuel injection swirlers. There are two pictures shown. One is a full one, another cut one. See how much complicated it is, and this is done in 2 weeks against 6 weeks in other methods, and significant cost reduction and also minimum 50% less time. Okay, and increased robustness, and particularly no joints, no braces, or no assemblies. Next, please. So that is highly complex systems, highly complex parts can be produced. This is electronic manufacturing. These are the companies which are using additive manufacturing into their R&D. Next, please. And coming to other general applications, jewelry applications. So civil engineering applications, architectural applications, they are using this additive manufacturing for producing models, miniatures, before going for actual constructions or otherwise stadium, etc. So in jewelry industry, almost all producing latest designs are possible only with the 3D printers. Next, please. So these are oval models, like a big stadium used to be built. So initially it is built with the 3D printers. After that, we use this model or miniature to enlarge our 1:1 scale in the real time. Next, please. So consumer goods. What what is that? Some messages are coming. Okay. Consumer goods. So like here, interior model holy goat chairs are there. So looking at these type of consumer goods, etc., what we are coming to conclusion is that the design is a problem. Manufacturing is not a problem. So you have idea that can be manufactured. Okay, next please. So see, this is the lighting system. So if you look at the first all three figures, and this is the concept. You are having different concepts, and this is possible with the 3D printers, which is not possible by conventional methods, conventional manufacturing methods. Next please. Lifestyles. Okay. So see the heel of that heel of footwear is sometimes no we may manufacture manually, but it is very difficult to get the repeatability. So here once it is produced in 3D printer, so 100% you will get the same repeatability. Next please. Pendants. So why I'm showing here the complexity and design which are possible with the 3D printers. Next please. So some of the projects we have done at Usman University. This is the cash counting machine, which we made into 3 parts and assembled. So middle one part, left one another one, 2 lefts are 2 parts and middle one is 1. Okay, 3 parts we made into 1 part. Okay, next. So these are all real parts. Okay, next. Okay, this is the after assembly, and this is a cash counting machine, which is we have done it for Acura company, and this product must be able to adaptable or compatible with the other assemblies like electronic machinery, PCB, etc. They are going to install. What we have made it only outside the casing. Next. So this is another electronic gadget. So that is a handheld computer or electronic swiping machines, credit card swiping machines are made like this. But here the challenging is here, we have to make in such a way or build in such a way that all other parts also must be interacted with this and within the permissible limits and tolerances we have to manufacture. That is the challenge. Otherwise, it is going to be wasted. Okay, next. So we have made one component for the Cadbury. There was a Cadbury celebrations on the occasion of what you call one second, this bat is going to die. I will put it. So the Cadbury celebrations on the occasion of that, this boy was not having 2 hands, and this boy hands are scanned and produced by 3D printers, which is situated in our lab. Left side, you can see those are the hands prepared or built in our lab. And after that, in Bangalore, there is a circuit, electronic circuit, which is installed with sensors and all, so that when his sister ties his Rakhi, that day he felt that no, his sister is tying a Rakhi. So it is a simply concept made by the Cadbury India, and it was successful, and it was built in our laboratory. Just 1 minute. So this was a challenging and interesting and satisfactory results in our lab. Okay, this was successfully installed and also demonstrated. Next, please. This is another component which is made for the DMRL, the Defense Metallurgical Research Laboratory. And they have given us this project because our limitation is only 200 by 250 by 330 in the polyamide Farmiga machine. And we made into 4 parts and then we assembled. This is we can say, a bulletproof jacket for the Indian Army. So this is made first with the powder. There's a plastic one. So once it is validated, then they go for manufacturing of this bulletproof jacket with the metal. Next, please. So this is a titanium-based alloy aerospace product. The application is confidential, but just I want to show how it. There is a second picture you can see in the bottom. There is a crack produced in the vessel because of the excess oxygen present in the chamber. And it's very, very challenging to produce parts by using 3D printers. And it requires zero oxygen in the chamber, and all levels must be like at acceptable levels. Otherwise, and it costs more. Titanium cost is very high when compared to other metals. That's why. So these are all failed component. So right, first one is successful and the second one is failed one. Next, please. So no boundaries for prototypes. So that means whatever the idea you have in your mind, that can be put in the form of a 3D CAD model. That means are you able to put your idea or innovation into 3D CAD model data or not is the question. Once it is able to put in the form of 3D CAD model data, so manufacturing is not a problem. So earlier there was a problem with manufacturing. Now the manufacturing is not a problem. The design is a problem. Design means how you are going to put, or is it represented in the form of 3D or not. That is important. Otherwise, so manufacturing is not a problem. Next, please. So the conclusion from my lecture is we can interact more on the question answers. First is, let me conclude and then we'll discuss. So first is, the building process affects the quality of the product. So building process. So whether it is which type of technology you are using, what type of process you are following, that affects the quality of the product. The quality of the part built through 3D printing is assessed by its dimensional accuracy and mechanical properties. So the process and the method and the technology, what you are using, whether what are the applications you are going to, for what application this part going to be used, that is also very, very important. For example, so aerospace part, how much porosity is permissible, what is the strength required, and what is the dimensional accuracy is required. So all this can be assessed. And the mechanical properties, like all mechanical properties, so that should be assessed. Then only it is passed, and then we can use it for applications. The X-ray tomography has emerged as a uniquely powerful and a non-destructive tool to analyze defects in additive manufacturing. The use of X-ray tomography to visualize pores and defects in the parts prior to mechanical testing. See, this is very, very important, this X-ray tomography. Though we are happy with the building, but we need to check whether the soundness of that product. So by using this tomography technique. So it is a non-destructive technique, and which is popularly known, and without this they will not accept, though you are building. Okay. So now presently in the area of 3D printing, research is going on to build artificial organs and tissues. So far we are talking about building of artificial organs like the liver, heart, etc. But it is only in the research level. But tissues, for example, tissues. In the case of tissues, the parts, because of the accident, a person can be removed lot of skin. So that's the skin can be cultured, and the skin can be replaced in the layer by layer technology on the wound. So the wound can be healed very quickly. Similarly, in US and other countries, they are working on production of organs with artificial organs with the 3D printers. Only thing is material is important. So it involves microbiology, biochemistry, and if that material is going to be emerged or otherwise invented, with that material we can go for artificial building of artificial organs. But in Usman University, what we have done, we have created a artificial heart, with mechanical movements. So like vibrations and all we used, and then pumping of capacity and all we have calculated and we have done tested, and it is under trial now. Almost 60-70% of the artificial heart building is completed, but tested. But only thing is we are now working on how to reduce the size that organ into our actual size. So with this, no, there are two sayings. I already spoken on this. Presently, it is olden days now. We used to say the manufacturing-driven design, but present saying is that it is a design-driven manufacturing. That means design is a problem, manufacturing is not a problem. But earlier, manufacturing was a problem, design is not a problem. So now manufacturing design driven. That means whatever the design is there, that should have been manufactured. But dictation was earlier dictated was manufacturing. Now dictating is design. That means manufacturing limitation was eliminated with 3D printers. So hence no boundaries for manufacturing, irrespective of the complexity. So there are three important things you have to remember. One is additive manufacturing produces parts with highest complexity. Next, without any assemblies or almost less assemblies, and rapidly producing. Within no time we can produce. So these are the very three important things. But you may ask whether it is a cost effective or when compared to conventional. Definitely it is not cost effective. It is costly, but its complexity, its what you call time for reduction of the product's life cycle is very important. And once we produce one particular part, that part can be used for producing lakhs of parts in the case of castings. So in that way, it is much useful. And in the case of biomedical applications, you name any part of the bone, human bone, are being produced by only 3D printers. Okay, knee joint, jaw, teeth, any part. Okay, in future, we are going to produce even tissue, hearts, artificial heart, etc. So that is the area. And in civil engineering applications, we are constructing the buildings with the help of 3D printers. And in Bangalore, with the help of 3D printer, there is a post office built. In other areas, small bridges, other foreign countries. In IIT Madras, there is a startup which produces the concrete, that is civil engineering 3D printers, etc. And definitely it is going to be a new area for all types of engineers: biomedical engineering, mechanical, civil, electrical, electronics, whatever it is. So it is a interdisciplinary, and the course is also offered as an open elective for many branches in Usman University. Other than mechanical, all 5 branches have taken, and maximum takers are from computer science and civil electronics. So with this, I will stop here, and I will be here for answering more questions from all the audience. I will stop the sharing and I request the Ashit Kumar, ask one by one. You can unmute and ask me doubts on any other topics, even which I have not covered yet.
Thank you very much, Professor Venkatesh, for such an insightful and enriching session. Now, participants, if you have any query, you can direct us to our speaker, or you can write in the chat box. Participants, do you have any questions? Sir, we have one question in the chat box.
What are the biomedical reasons? 1 second, I will just open it. What are the biomedical recent trends of mechanical processes?
Materials, yes, sir.
What are the biomedical recent? That is gone.
No, what she is asking, sir, what are the biomedical recent trends of materials for prosthesis?
Processes.
Yes, sir.
Yeah. We are extensively using in processes design, no? Surgical and mainly in the biomedical applications. Right now, we are using for any part of bone replacement, surgical planning, bone replacement, and building of implants. These areas we are doing.
Any more question from participants?
Okay. In the post you can see. What is that? Sir, can you please share the feedback link? Okay.
Sir, good evening, sir.
Yeah, good evening.
Sir, this is Dr. Sujan. I'm also one of your student from Osmani University, sir.
Yeah, very good. Okay.
Sir, I would like to know about that. What are the challenges while we go for the metal 3D printing process? At the same time, how we are going to be maintain the same strength and mechanical properties as well as the thermal analysis after manufacturing of the component? After manufacturing of the component.
Yeah. The biggest challenge is, I told you, I was shown SLM produced part which was actually cracked. There are two areas. So we need to maintain the oxygen levels in the chamber as desired. For example, if you are going for building of titanium based powders, sintering or melting of titanium powder, we need to maintain oxygen almost zero. So to maintain oxygen zero, we need to send the argon, any other inert gases. So particularly argon. So maintaining zero oxygen in the chamber is one challenge. And continuously up to complete building of this, we need to monitor. So if it is increased in the oxygen levels, their distortions are taking place. Definitely, it is going to affect your mechanical properties, thermal strength, etc., etc. So that is the biggest challenge in the case of metal powder 3D printers, particularly SLM and SLS.
Okay.
And we have SLM in the system, but right now it is under, I think there is a pump issue is there. We have faced this type of problems in the SLM machines. And there is a thermal stress analysis. There is a software before producing. We can also initially find out the supports and the thermal analysis, etc. And after that also we can compare with the what you call mechanical strength and other one.
First of all, we have to predict it. After that, we will
Yeah,
go-
yeah. We can predict with simulation through softwares,
simulation. Then we can go for that testing.
testing.
Okay, sir. Okay, sir. Thank you, sir.
Next, please. Any questions?
Any question from participants?
And for the information of all the participants, there is a National Center for Additive Manufacturing, NCAM. So it is the only 3D printing center or an additive manufacturing center in India that is situated in Engineering College, Usman University Technology Development Center. They are also manufacturing powders which are used for metal sintering machines or SLA machines, and they have 6 startups. They are also producing the powders, and they are using for their own machines and as well as exporting. And they have different types of machines, and it's like a workshop situated in the Engineering College campus, the Technology Development Center. And the students are utilizing for project work, research work, and even internships. So that is for the information of all the esteemed participants in this ATAL FDP.
Thank you, sir, for sharing this also.
Yeah.
So if there is no questions, then once again, sir, thank you very much for sharing this.
I expected more number of questions from the participants.
Yes,
I think
sir.
they are now maybe hungry and they are leaving.
Yes, sir. I hope it's a